Okay, everybody. Uh, you might hear I have a little bit of a cold, so it might not be as stellar as the past couple of weeks. But I'll do my best to get things across. So we're week 4, and so you remember that next week we have another session, and then you have academic development week. So there'll be no taught session. I'll just post some things on the blackboard. So it'll be a very good time for you to do catch up if you haven't done any of the exercises yet, or you've not done all of them. It'll be very good to use that time to catch up with any of the lectures or exercises which you haven't been able to do thus far. So last week was all about ANOVA and its associated nightmares. We talked about ANCOVA and MANOVA. Today is going to be all about correlation and regression, and ANOVA will return next week when we talk about more. You remember that I talked about type 1, type 2, type 3 errors. So next time we're going to talk about even more complex ANOVA things like 2x2 interactions and how to test those. So today, again, part of it might be things which you've already seen during your undergraduate. It will be correlation and regression. We'll talk also about the assumptions of underpinning regression, and then probably you haven't seen logistic regression. Does that ring a bell? Have you seen logistic regression? Yes, you have? Okay, so some of you might have come across it, but it's not something which is always part of the curriculum, so it might be something new today. So after today, you're able to complete the following sections. You're able to complete the section on correlation, the section on regression and its assumptions from your assignment. You'll be able to make even better plots and toy around more with making plots, and you'll be able to complete the section on logistic regression. That just leaves the bits to do with 2x2 ANOVAs, and then you're able to do everything for assignment 1. So alongside the exercises, which really map on close to what you should be doing for your assignment, you're able to basically, from week 1, you're able to complete chunks of your assignment. So now back to the meat, so to speak. So we're going to talk about Pearson correlation. A correlation is mostly the first step. You want to find out the strength of an association between two continuous variables. So again, some of these things are formula and things which I have to give you sort of for your reference. And so these are from your undergraduates, the sample correlation coefficient. And you might remember that it translates to the covariance divided by the geometric mean of the variances. Yes? And so you can read back to your notes, or I've put in a link if you want to read more about the formula behind the Pearson correlation coefficient and what it's all about. The assumptions, as with any statistical technique, I have listed here the most obvious thing that you have independent observations, because that applies to nearly everything. So if the observations are not independent, then you run into problems. So it needs to be continuous. So you might have heard, or you might remember, Spearman and Kendall correlations, or like Kendall's tau, Spearman rho, as like alternatives for when you have ordinal measures. Just as regression and some of the other techniques, we require normality. So you remember that from the data source also, like if you have an outlier, you can have a very strong correlation that's driven entirely by this outlier. So you also have the assumption of homoscedasticity. So it's the same as Levine's test for variances. So it's the same type of test that we had with ANOVA. Homoscedasticity or heterogeneity is the same type of terminology. And the pattern has to be linear. So you remember again from, if we look back to the data source and those quartet type of graphs, so we could have the same correlation, but it could have very different underlying patterns. It could be nonlinear, it could be like this curvilinear pattern, or it could be driven by an outlier. So that's the assumptions for making inferences about correlations. Now, a particular pet peeve of mine, which I have to tell you about, is that if you sample the entire population, then there is no probability. So if you did a correlation between, let's say, the height of people in Amsterdam and how much milk they drink, and you sampled every single person in Amsterdam, then there is no probability. Like, you know what it is. You know the perfect relationship. So we use inferential statistics because we usually don't have the entire population. We draw a sample, and then we want to make inferences to the entire population. But there are cases where you have the entire population. So if you don't want to generalize beyond the school, but you sampled every single pupil in your school, then there is no point in doing inferential statistics. The correlation coefficient is the correlation coefficient. The probability doesn't exist. The same applies, for example, if you have data, for example, on all 50 United States, and you find a correlation between, let's say, homicide and deprivation or some other measure, then there is no probability. That correlation coefficient is fixed. There's not going to be a future United States, which is an independent data point for which you can make inferences. So that's a particular pet peeve of mine. So I hope to never ever see that in one of your papers, because then I'm going to write a nasty letter to you now. So you should also remember that correlation is not causation. So, but usually it's the first step. If there's no association, then usually some of you will be unable to do experiments. So you will only have observational data. And so if there is no association, then that's sort of where it breaks down. So just because a correlation exists doesn't mean that there's a causal pattern in it. You remember all sorts of associations. There's even a website where you can find correlation between the number of engineers and chocolate consumption and all sorts of other things at country level. So you can easily get spurious associations. That doesn't mean there's a causal pattern to the data. But exciting things, this might change in the future, because actually, very cleverly, some computers might be able to tell us where correlations actually do inform causation. You can read more about in this link, but basically it works if the noise of one variable influences the noise of the other variable, then likely that one is exerting a causal influence on the other one. And via some very, very clever simulations, for example, on housing prices and the size of the house, people are able to make inferences as to what it is. Okay, so you can have a look there. So how would you go about getting your correlation done in R? So I'm going to call a dataset, and you might remember this dataset because the dataset, if you've done your exercise, which has the sepal width and petal width, for flowers, and so it's, perhaps I shouldn't be doing this, but I make a new object called iris, because there's also iris in the dataset. You call it iris2 or iris3, whatever you want. And then the correlation is nothing more than the core command, and you remember that you can use the square brackets to denote positions in your dataset. So this would be the first column and the second column. So that would be sepal length and sepal width. That would be correlated. And so that would be you could also call them directly via the $sign. Yeah. So just by using their name, and you get see that's the same type of value that you get. Luckily, yeah. You can also change the method. So if you have ordinal measures, you can say, so by default it's a Pearson correlation, which is the interval one. If you need a Spearman or a Kendall, you can change by saying method is Kendall or method is Spearman. Yeah. So that's if you need ordinal things. So you might have spotted that this is just a correlation coefficient. So where are our test statistics and where's all the other blah that we usually get, like our t-tests and all these other things. So if you want that, then we use core.test rather than core. That's because usually also we want to just have the correlation, because that's something we use for computations later. We don't care about the test per se. So that's why R, as the default for core, only will print the correlation value, not the test. So core.test, again using the $signs for the association. In this case, you can change also the confidence interval. So you can make a 90% confidence interval, or an 89% or a 67%, whichever number you like. And that will print something that is more familiar to you, like it will print the actual value, which is roughly the same as we had before. Yeah, so it's the same type of value that we had here. And it will print as the 90% confidence interval, it will print as the t-test, and the p-value associated with this. And in this case, there is no significant association between sepal length and sepal width. Perhaps it's the illness, but I'm speaking very fast, so if I speak too fast, slow me down and raise your hand. So how would you write this up? So you would write something like the Pearson correlation between sepal length and sepal width was not statistically significant, and then you would report the correlation, the value, and the p-value. Yeah, that's an APA-style type of write-up. Unfortunately, this isn't very clear on this because it's sort of downgraded, but you should be able to see it clearly on your thing. So again, by now you're able to make all these pretty charts because it's things which you've practiced. So what we do now is we make a plot. I remember that we call the data. We say which one is the x and the y. We can color it by species to make it prettier. So these are the species. We can then also add geom jitter, and geom jitter is just to make sure. Occasionally on scatter plots you'll have points that fall in exactly the same spot, and you wouldn't be able to tell. So geom jitter just adds some random noise to those data points so they don't overlap in your plot. So what we then do is we add a grid because we want to split it out by species. So that's the next step. So this first builds our base plot. Then we add a facet grid, and so that basically splits it by species. And then we add a linear fit through those scatter points. So that's those lines. And then we can change the colors. So I picked dark tulip color. You could pick your own little palette, or you could pick individual colors as to what you like. And then the next step manipulates the labels. So it says, which you can't see because it's sort of cut out. Well, you can still see here, sepal width. I'll try and reduce it in the next version so it fits nicer. Sepal length and sepals, and you can change the theme of your chart. Remember, you can have Google Teams, Excel Teams, Stata Teams, whichever one you think looks pretty or whichever one your supervisor wants it to be. Yeah. Any questions so far? So this is again something which you have done before because you played around with these charts, and you're gonna do. This is how you illustrate, for example, the association by each group. So again, this is where R might actually save you some time. We can make formatted tables. So in this case, we want to make a correlation table, and we do that. We first use dplyr to select from a database. We don't want to have species in there because species is not a continuous variable. So that's why we don't want to have it in our correlation table. So this will drop species from the dataset, and we'll make a core table dataset. And then we use apa.core.table, and then we'll make a correlation correlations document. Let's see if I can show you sort of what that would look like. Let's see if we go to teaching, lecture 4. Let's see how fast Word is in opening. It's thinking about it. The wheel of death. So there's nothing to do with my PCs, everything to do with Microsoft Office, just telling you. So this is sort of what you would get. So again, this is one line, well, if you think of it, 2 lines of code, and you have a formatted correlation table from your data, which you can then put in your report. So that's quite nice. So it has the mean, standard deviations, and correlations with these confidence intervals. Again, you can manipulate and change things. In our case, these are just the variables as delivered from the data set. So you might want to change those by using underscores or changing it, so or edit them further in the table. So a nicely formatted table straight for your report, whereas otherwise in SPSS you would have to do copying, pasting, fiddling around with the margins to make it look pretty and all sorts of other things. Yeah. So hopefully more and more I'm trying to sell you as to, like, especially if you have to, for the next 5 to 10 years, make lots of correlation tables and format them. This will save you some time from doing boring jobs like formatting tables and dealing with those. Any questions? Back to the presentation. So what we can also do is we can make a correlation plot, and that will basically have the same information as that table, but it will sort of color it based on the strength of the association. So we call a package called GG core plot there. We make it into, we calculate the correlations and call it core matrix, because we need to input that. So we need a correlation matrix in order to do that. And then we can make that thing, and we can just type is lower, sort of means that you could have it flipped, because you remember that correlations are symmetrical. So otherwise we could fill up all those quadrants with values, but because it's symmetrical, it makes sense to only show half and not show the ones where it should be 1. Yeah. So because on the diagonal it will be a perfect correlation, so that's why it's not shown here. And you can add some labels to it. Again, this will not be visible from here, but the color intensity here on this thing will nicely say how positive or how negative the correlation is. Okay. So other packages exist, and so there's many ways to plot this. And I have a tutorial at the end referenced by Willem, so you can have a look at those for some other packages and some other ways which you can muck about with correlations and make some pretty plots if you need to. So we're going to play around soon with a new data set. So these data sets are based on Fox and like Fox 2002. So they're books on regression, if I'm not mistaken. So if we call car data, we have a prestige data set in there. It has a capital prestige. So we're just going to call it prestige with a lowercase just to be annoying. And in that data set, we have data on education. So as you might imagine, the type of prestige, what sociologists and other people sometimes care about is coding lots of jobs based on their prestige. So you just ask a bunch of people, how prestigious is it to be a nurse, to be a teacher, to be a doctor, a lawyer, all these other things. And they do that because they care about social class and perceptions of social class, and that's why they have compiled these type of data sets. So education is the average number of years of education associated with that job. You have income, the average income associated with that job. You have the percentage of women in that occupation, typically. The prestige rating for that job. Census, so this is just whether the code which maps on to the occupation. And the type, so whether it's professorial, white collar, blue collar, or missing. Yeah, so some type of classification as to whether it's manual labor or not manual labor. So what I would like you to do is try to load your prestige dataset and make a correlation matrix with all the continuous variables. So remember, some of these are not continuous because they're, for example, type is not continuous because it's categories, yeah? So it's not a continuous variable, so everything which has numbers in it and can be interpreted as a number, so don't just look at numbers, but the numbers might also be codes. So everything that is sensible as a continuous number are the things I would like you to use, and I would like you to make a correlation matrix with all the continuous variables. So you remember that you have to use filter or select or some other type of things to select the type of things that you're going to need. And you could also remove those by remove NAs if you wanted to. And then I would like you to export that as a table like I did, or so you don't have to do both. So either make a plot like this GG correlation plot, or I'd like you to export the data like in a table. Yeah, everybody sort of knows what they have to do.